Okay. Good morning, everybody. And here we start again the important lectures that we think for great permanent mathematicians to give talks on literature and history of mathematics. We had a very successful talks before the summer. So we begin again. And now I'll turn this seminar to Bill Minicosi, who will chair the session. Bill.
Thank you. Good morning, everyone. So it's a great pleasure to introduce our next speaker. So Camillo De Lellis from the Institute for Advanced Study will speak on area minimizing integral currents and their regularity. Thank you, Camillo.
Okay, thank you very much for this prestigious invitation. It's a beautiful occasion to actually give, I think, at least my ambition would be to give a bird-eye view of a subject which has been very successful in the last 70 years and which has fostered a lot of developments in modern mathematics. Okay, so what I want to start with is the classical Plateau problem, which is named after a 19th century Belgian physicist who was interested in subfilms. And mathematically, the problem is the following. So you're given some contour, gamma. So let me not be too specific on what this contour is. And let's say for the moment, of course, he was interested in a contour which was in our Euclidean space in 3 dimensions. But we're in general going to consider contours of any dimension which are going to be in some space. Maybe let's just restrict our attention on the Euclidean space. And let's say this contour has dimension m. And loosely speaking, you could just think about having an m-dimensional closed surface, which is smooth, but you might actually be interested in more general objects, which are maybe less regular than that. Okay, and you are looking for, so we look for m+1 dimensional surfaces. Right, and actually, so that I don't get confused with my own notation, maybe let us go back and say, well, the dimension of the contour is m-1, and the dimension of the surface which spans it is m. So we are looking for m-dimensional surfaces which span gamma and minimize the area. Or let's say the m-dimensional volume. Okay, and mathematically, this immediately raises all sorts of questions, which would be what actually should you understand as a surface which is spanning this contour? If everything is smooth, you could simply restrict yourself to consider smooth m-dimensional submanifolds whose topological boundary is given by, or whose differential topological boundary is given by gamma in the sense of submanifolds with boundary. And then you would have the usual m-dimensional volume, which is the volume induced by the Riemannian metric on the surface, which is induced by the Euclidean space. But you could actually consider more general things. I mean, why not? In fact, if you actually refer to the situation of subfilms, you will see in several occasions that actually true real-life subfilms do develop singularities, so they're not necessarily regular surfaces, right? So therefore, the first questions that we actually are going to ask is what is for us a surface that should be considered? And secondly, what is actually the m-dimensional volume that should be considered? Okay, and historically there have been several answers to these two questions, and I would just say that there's not really a way to say one answer is better than another, at least in my humble opinion. So what is really happening is that in a lot of situations, I think you should ask yourself, what exactly do you want to achieve with your theory? And depending on what you want to achieve, certain frameworks are actually better than certain others. And I don't think there's like, a universal one, which is fully satisfactory for whichever thing you want to do. So for instance, you might actually want to really address a model for the physical problem that Plateau was considering back in the 19th century. And in that case, you certainly want a variational theory, which is capturing what are like, the solutions that you experience in real life when you're dipping a wire into soap water and you get out and you get a soap film. So that might be one goal. But of course, if you have that goal, it doesn't make that much sense to consider a situation in which you are like, in a higher space dimension. But you might have completely different goals, which is, for instance, understanding the structure of some geometric objects. And in that case, minima surfaces of a certain type serve as very good models for instance, filling manifolds and things like that. And so let me just say that, broadly speaking, there have been several approaches to answering these two questions in the past century, and there's actually even research going on right now on what is interesting to do in this area. But let me just say that all the like you could sort of classify these questions in three broad way of approaching the problem. Okay, so let me just say philosophically there are three broad categories, not in the sense of category theory. I mean, like, in the philosophical sense of approaches. And let me start actually with the first one, which the people actually call the, which in the literature is usually called the parametrized approach. This is historically the first one which proved successful, and it was successfully implemented by Douglas and Rado with contribution of several, who were using like contribution of several other people, like, beautiful mathematics developed by, for instance, in the literature of conformal transformations and in complex analysis. And in the parametrized approach, you just take the point of view that actually your surface is parametrized over a certain, so it's the image of a map over a certain space of parameters. For instance, in the Douglas-Rado approach, what you could insist upon is that you have a model surface sigma, which might be, for instance, the disk. And you're looking at maps U, which are going from sigma into your Euclidean space. And let's say such that U at the boundary of sigma restrict as maps onto gamma, which are an homeomorphism. Okay, and now if you have a little smoothness of U, and we're not too interested in this moment to just exactly say how much smoothness you need, you can compute the volume of the image of sigma with the classical formulas, and you actually want to minimize that that function. Okay, so that is one possible approach, and that's actually not the one that we're going to be mostly interested in. As I said, it has been pioneered by Douglas and Rado. Okay, so there's another approach, and let me just say this in a sense would be something like what I would call a set theoretic approach. And that's not really a name which is encountered in the literature. This is more like, my way of calling this type of framework. And I think the pioneer in this was Reifenberg. And the idea in these sorts of approaches is that I actually allow any set. So any set for me is going to be like a good competitor as long as I have a good notion of what it means to span gamma. For instance, one thing that you could just simply imagine is like I restrict myself to sets sigma which span gamma, by meaning that, for instance, gamma could be homotopized if it is going to be a curve, could be actually homotopized to the trivial curve, to the trivial point. Okay, so that doesn't turn out actually to be the most successful way of looking at things. In fact, what Reifenberg was looking at were general closed sets for which gamma inside the set sigma is homologically trivial in the Chesh homology. Okay, but I don't want to go into that either. So the takeout in this case is that you're actually allowing any set at that point. You should decide actually what is the m-dimensional volume of any set. And for the m-dimensional volume of any set, you have the Hausdorff measure, for instance, at disposal. So it's kind of natural. You have a natural concept of measured theoretic volume. Not so clear, though, what it means to span so it's more challenging to understand what it means to span gamma. Okay. Then there's going to be the one which actually will be the focus of this talk today, and that is what I would call a functional analytic or homological approach. Okay, and I will talk about, I will talk extensively about this. So let me just, like, for the moment, not focus on that. And to my surprise, actually, there was sort of new wave of interest in the real physical Plateau's problem, which was ignited by recent works by Jenny Harrison and Guy David. And those works were more on the set theoretic approach, but some people, and they want to advertise their work, came out with a very new, interesting point of view actually on the Plateau problem. So, and there are very interesting works by Maggi, Scardicchio, and Stubard, and subsequent works by King, Maggi, and Stubard. And their point of view actually is very sensible from the physical, from the physical point of view of wanting to actually model the original problem of Plateau. And their point is, for instance, starts from a very simple observation, that is that there's certainly something wrong if you want to understand a good physical model for subfilms, and you just say that what you have to do is minimize area among all surfaces which are spanning a given contour. So let me just give you a very obvious reason why this is wrong, and even a child could actually observe that. The problem of minimizing the area among all surfaces which span a given contour is scaling invariant, okay? So now try actually to build a subfilm which is I don't know, larger than 10 meters, and see how you would actually hilariously fail. So it's quite obvious that there's something which is not scaling invariant in the very nature of the physical problem, which is dipping a wire into soapy water and trying to understand the subfilm which is getting out. And so one very interesting point of view of these guys is that if you want to understand that problem, what seems to be actually the physically relevant parameter that you are completely ignoring is actually the thickness of the film. So the thickness of the film is not zero. It has some thickness. And if you actually want to model that problem, you should rather see the Plateau's problem as a kind of physical limit as epsilon is going to zero, where epsilon is the thickness of the film. And that actually still leads asymptotically to the classical Plateau problem. But if you approach things correctly, you're actually seeing over there some indications of, you know, which type of approach you should use, even in the classical Plateau problem. So let me just say that this one is brand new, and let me just dub this some sort of mathematical physics approach to having a sensible variational model for your problem of finding salt films. And they have a very, very convincing point, actually, in their papers, at least very, very convincing for me. Okay, so what I actually want to focus today, though, is this third part. And let me start with the easiest situation. So let me start with the codimension 1 case. Okay. So what would I naturally understand in the codimension 1 case as, you know, a surface which is trying to bound something? So if I had a smooth surface, so that, you know, these 2 points, let me go actually to sort of the silly situation in which my gamma is actually 0 dimension, right? That's not that interesting. But anyway, so my point, I mean, my boundary gamma would be 2 points. And then I'm just looking like, you know, at a connected curve. Okay. So one way I could actually understand this, if I'm sitting inside some, you know, some domain U, is actually to think that my connecting curve is bounding a set, right? And it's the boundary inside your domain U of a set omega, okay? So I can understand at least certain type of surfaces of hypersurfaces in the Euclidean space as boundaries of open sets, okay? Or at least as relative boundary of open sets in some other open sets. That is a very interesting point of view. By the way, it obviously excludes some competitors. So for instance, you certainly cannot recover something like this, configuration over here. So like, you know, a triple junction as the boundary of an open domain. Because, you know, if you were to decide, for instance, that your open domain is this one, you just see like only 2 legs of the triple junction. So it's an interesting point of view, but it's an interesting point of view which is not like encompassing every possible competitors that you might want. Anyway, it's an interesting point of view, and you could just ask very well. So let me restrict my attention to hypersurfaces, which are boundaries of some sets omega. Okay. Now, how regular should actually omega be at this point, right? So if you have a nice open set, you can just say, if you have a nice smooth open set, you can just say from classical differential topology that its boundary is going to be a nice C1 submanifold or C infinity submanifold. But do you really want to do that? Or maybe you want to actually admit surfaces which have quarters and so on. So what is actually the most general type of surface that you can admit, which has in some sense a boundary which has finite measure? Okay, so one would be tempted actually to say that for this, you would like maybe to define open sets whose boundaries have finite Hausdorff measure. But that turns out not to be a very good idea. So because that class is not closed under natural convergence. So it doesn't serve you that well. And what actually turns out the most efficient approach to this concept is, or at least what is believed to be the most efficient approach, is the theory of so-called Caccioppoli sets. Okay, so Caccioppoli sets, in a sense, could be thought as the largest family of measurable subsets of the Euclidean space whose boundary in a suitable, and that's why it's actually going to be a functional analytic approach, which in a suitable functional analytic sense have finite perimeters. So another way actually to call Caccioppoli sets that you will see in the literature is sets of finite perimeter. Okay, so now let me make, since this is also like, touching on the history of mathematics, let me actually make a historical remark over here. So back in the days when Caccioppoli was actually working on this problem, so there was a lot of research around on what should be actually the right notion of generalized surface. I mean, how you should enlarge the class of smooth surfaces like coherently. And there were works by Whitney, but there were even previous works by classical mathematicians like Hausdorff on how you should actually measure the content or the m-dimensional volume of a general set, or Bezikovich, who actually came out with the concept of rectifiable one-dimensional sets and who built up a beautiful theory. So there were all these concepts, and Caccioppoli was a sort of outlier in the mathematical community, because he actually had the point of view that the sensible for him definition of a surface that you should take and of boundary of generalized sets that you should take is just the following. You should take a general, you should just take a general, say his definition of this. So Caccioppoli sets, in Cacciopoli's definition. So you take any measurable set U, so let me just say U is in R n plus 1 measurable. Okay, and you define the perimeter of U the following way, which for him was like, the variational way of making sense. So I have a nice definition of what the perimeter of U is. If U is smooth, that's the category where I actually know what the perimeter is. Then I want actually a topology on all sets, and the topology on all sets that I can take is like L1 conversion of the indicator function of the sets. And at that point, from a variational point of view, it makes sense to actually look at the lower semi-continuous envelope of the functional that you're looking at. So if you take this point of view, the perimeter of U should be defined as, the inf over all sequences of approximations of the liminf as k goes to plus infinity of the perimeters of the UK for all UK which are converging to U. So for all UK such that the symmetric difference of UK and U is going to 0 in the m plus 1 dimensional Lebesgue measure, okay? So you take all possible approximations by sensible sets, and now by sensible set, you can take your pick. So for Caccioppoli, it was actually polytopes. Maybe nowadays you would more take like, I don't know, smooth sets. So let be like Caccioppoli, then this would be like polytopes. And then among all possible approximations, you take like kind of the best one. I mean, the one that has least perimeter, okay? And of course, if you have such a definition, you should check A, that this definition is consistent with the original concept of perimeter. That's maybe not too difficult, but then you want to do something with this, right? So you want to prove that this relaxation gives you some structure when a set U has finite perimeter. And that's where he got completely stuck. I mean, this was a very nice idea, but he wasn't able to actually build any coherent theory out of this, which would give you something nice. So if you actually go on Matsainet and see at the mathematical reviews of his papers, he got completely trashed. And one of the people who was most critical on him was L.C. Young. L.C. Young just said, all of this is actually nice, but you cannot connect it to any known mathematical research. It's just completely isolated from all the rest that we know. And you cannot actually make anything with this theory. So it's maybe a nice idea, but that it is what it is. Okay. So that was the story with Caccioppoli, and it is actually said that Caccioppoli, at least that's what I heard in Italy, is that Caccioppoli was in part also depressed by this very bad evaluation of his work that was given by the mathematical community, especially outside of Italy. But then here comes De Giorgi, and what De Giorgi did is he actually took Caccioppoli definitions, and then he built a perfect theory, which was actually connecting with the works of the other mathematicians It was amazingly powerful and would give you the existence of minimizers for the Plateau problem, actually of vary in any dimension for hypersurfaces in a very efficient way. So what he was actually able to show is that you take Caccioppoli definition and U has then a concept of measure theoretic boundary and the measure theoretic boundary must be actually understood in the functional analytic sense, meaning that if I integrate over U the divergence of a vector field X, which is smooth, I'm actually able to find a substitute for a Gauss theorem, Gauss-Green theorem. So this would be like equal to the integral over the boundary of U of X dot nu. And I'm just putting actually the quotation marks because you have to interpret this in the correct way. But what was very powerful in the George's theory is that, yeah, I mean, you have to interpret it in the correct way, at least functional analytic. But after you've done that, actually you're really able to identify a rectifiable set. So something that actually people were studying before independently, which has finite Hausdorff measure, something that people were like, working on independently. And the perimeter of your set U is actually going to be exactly the n-dimensional Hausdorff measure of this rectifiable set, for which actually even this integral over here has a very classical interpretation. So the only thing that will happen is that this boundary here, U, is actually going to be very rough, but otherwise it's all going to be sort of the usual integral over a surface of, the normal times the vector field. So he got everything in a stroke. So he actually revenged Caccioppoli's point of view. He actually showed that this is like a very sensible way of approaching the Plateau's problem. He showed that it connects to the work of all the other people who were like, studying generalized sets and building very elegant and powerful theories. And it's actually what is like still up to now considered one of the most successful ways of approaching the Plateau's problem, and which has actually had a wonderful number of applications in geometry, mathematical physics, topology, and so on. So you name it. And L.C. Young, so again, if you go on Matzainet, L.C. Young is actually the reviewer of one of his foundational papers. And at that point, L.C. Young in his review says, well, after the work of De Giorgi, we should actually reconsider our judgment on the work of Caccioppoli on a different light. So it actually gives finally justice to the fact that, yes, he was taking a very good point of view. He was probably taking the most natural point of view to actually approach the Plateau's problem from a functional analytic point of view, if you want. And actually, it's the work of De Giorgi that substantiates that point of view. Okay, so that is very, very wonderful. But of course, the first thing that you could say is, well, it's very nice, but it works only for codimension 1. Because as soon as we go in higher codimension, we actually don't have a framework for what it should be like to be the boundary of a set. Okay. But if we go in higher codimension, what we actually have, we have like, a homology and cohomology point of view. Okay, and one thing that we can do is, as we were integrating vector fields times a normal on the boundary of a set, or as we were actually integrating divergence of vector fields on a set, we could, on a general surface, integrate forms. And understanding what the boundary of a nice smooth submanifold, oriented submanifold is, for that you actually have Stokes' theorem, which is telling you that if you're integrating the differential of a form over, say, sigma, that is equal to the integral of the form on the boundary of sigma, okay? So you have Stokes' theorem in the classical setting. So in the classical smooth setting. And that tells you that the integral over sigma of the differential of a form is actually equal to the integral over the boundary of sigma of the form omega. Now, what can I do with this? Well, one thing that you could do, and this was like a point of view which was taken by Theorem, who was not interested at all in solving the Plateau's problem, but he was interested in like topological and differential topological problem. So Theorem actually proposed the theory of currents. And the current is just a generalized surface. And it's a generalized surface in the sense that you define a current as a linear functional on the space of smooth forms. Okay. So T current is a linear functional on the space of smooth forms. Okay, now the boundary of a current can be easily defined. If you want to act actually on a form, that's all you care when you're actually looking at linear functionals. So of course you can take Stokes theorem as a definition. The boundary of a current is simply the action acts on omega simply by evaluating the current itself on the differential of omega. That's very nice. Now you could actually wonder, what do I understand as total volume of a current? And that's also kind of nice, because you could imagine that, you could imagine that in the smooth situation, you have an inequality of the following type. The integral over sigma of omega is less or equal than the volume of sigma times the maximum of omega in an appropriate norm. So now here, that's actually, it's kind of subtle. If you were back to integrating over the boundary of U a vector field x dot nu, that would be much easier. So this actually can be read in terms of forms, but of course you would have just the inequality that the integral over x dot nu of the boundary of U is less or equal than, the L infinity norm of x, and then you would have like, the m-dimensional volume of the boundary of U. And this is the L infinity norm in the usual way. You just take the modulus of the vector field and you just take the supremum of that modulus of the essential supremum if you want to like work in a non-smooth category. So here you have to work a little bit harder, but somehow you could just say, well, the mass for me is the number over here which optimizes this this inequality. Okay, and that's very good, but you just have a drawback. If you take the Ram's original approach, you can actually take weighted surfaces, and maybe there's nothing wrong with that. After all, you could just think that, I don't know, you have a situation where maybe minimizers are like, tending of like, making a double cover of something, who knows, that is maybe possible. But the problem is that you can even take like, a rational portion of a surface or even real portion of a surface, like, take a surface and put actually a real coefficient in front of it. Instead of integrating over sigma, the form omega, integrate over sigma and then multiply by a real number. Okay, and that is not that good actually if you are willing to like approach the Plateau problem in a classical way. So like, what is exactly half of a surface? Do you really want that? Maybe you want it, maybe not. But certainly at the beginning, people thought that this was not something that you wanted. As I said, that Ram was not interested in the theory of in the Plateau's problem, but Federer and Fleming were. And they actually proposed integral currents. And the idea in the proportion of integral currents was to formalize the concept that you shouldn't allow real coefficients when you're actually weighting the surface. So how could you do this now? Possibly. So there are actually two ways you could actually try to define integral currents. Well, one way could be like Caccioppoli's philosophy. So take nice surfaces in the smooth topological sense, weight them with integral coefficients, and then close it in some appropriate topology. So there's one possible definition, which is like, like Caccioppoli style. there's another possible definition, which is just to say, well, let me just give you a definition hands-on. So a current T is integer rectifiable if I can write its action as a sum over I equal 1 to infinity. And now, okay, so first of all, for a nice current, what you would say is like, a nice linear combination, finite linear combination of, smooth surface weighted with integral coefficients. So certainly you want integral coefficients over here. Now, if you have a nice chain, what you would do is like, you would not take an infinite sum, but you would take a finite sum. I'm actually allowing to take an infinite sum. And of course, I would put like, the condition that that sum converges if you want. And then if you were a nice chain, you would actually insist on taking linear combination of smooth manifolds with smooth boundaries. But now I actually allow you to, first of all, relax the smoothness, maybe take only C1, and then I allow you actually to integrate over very bad sets, right? So, and here I'm going to have like the integral over EI of omega. And now EI are going to be inside some sigma I, C1 oriented submanifolds. I mean, it should actually, it should kind of ring the bell with what was happening in Caccioppoli situation. So in Caccioppoli situation, it was just saying, okay, I'm taking boundaries of measurable sets. Measurable sets can be actually approximated by closed sets. So as long as I can integrate on a set, I'm happy in the top dimension. I'm happy with taking the boundary of that if it has like finite volume. And now here, I'm actually happy to take like, very bad pieces of C1 submanifolds as long as I can integrate over them. So closed or measurable, because I can actually then use classical measure theoretic approximation theorems. Then I can actually put integer weights. I don't want to put real weights, but I can put integer weights. And then I can sum them up with an infinite sum. Okay. So now, before I go on, let me actually warn you. Federer and Fleming were doing this, I think, unaware of De Giorgi Caccioppoli's work, or if they were doing, I'm not sure how much they were aware that, this could be interpreted as a generalization. So unfortunately, I don't exactly know what is the answer to this question. And, maybe somebody who's like, older than me and has witnessed the development of this theory maybe could actually shed light on this. So I'm not claiming that Federer and Fleming were trying to generalize Caccioppoli De Giorgi, actually. But in fact, they did. So, and what happens in the Federer and Fleming theory is that there's, in their foundational paper in 1960, in this more generalized sense, there is a correspondence for everything that De Giorgi kind of proved in the codimension 1 case. And each of De Giorgi's theorem can actually be reinterpreted as one particular case of the Federer and Fleming theorem. So first of all, the 2 points of view actually coincide. So you can do Caccioppoli style by closing sort of nice linear combinations of surfaces with integral coefficients, or you could take the hard approach of having like a rectifiable what is called a rectifiable current. So and that is called a deformation lemma. Okay, so the second thing that is that actually this is a compact class. So so you have the compactness of integral currents. Well, it's a compact class as long as you kind of control the total mass of along the sequence, as long as you control the total mass of an integral rectifiable current, and as long as you actually control the total mass of its boundary, then up to subsequences, this is actually converging to an integral current. Modulo some technicalities, maybe you don't want to actually have things maybe escaping to infinity or stuff like that. And then there's the boundary rectifiability theorem. So the boundary rectifiability theorem tells you that as long as you have an integer rectifiable current, it has finite mass, and you just assume that the boundary in the sense of current has finite mass. The boundary is also going to be integer rectifiable. And that's exactly what I was actually pointing out over here in the George's theorem, that is a structure that if you just take Caccioppoli's definition, which would be you have a top integral current, because if I'm just taking at sets U's, like, you know, taking generalized m+1 dimensional manifolds with multiplicity either 1 or 0. And as long as I know that its perimeter is bounded in some appropriate sense, then the boundary of this set, which in the sense of currents correspond to having Gauss-Green by sort of identifying vector fields and forms, can be represented as really integration over nice, or at least countably many nice rectifiable or C1 or closed subsets of C1 manifolds, right? So the structure theorem that I was actually pointing out at this point is just a particular case of the boundary rectifiability, okay, over here. So you got all of this. It's a wonderful theory, and now all that you had actually in codimension 1, that is a very reasonable existence theorem for generalized surfaces. In the case of the Plateau problem, you have it actually in any dimension in codimension. Okay, so you see that there's, like, you know, an homological flavor in here, but then there was even another development which makes things even more clearly homological. So Fleming then defined even currents mod P. And, you know, you can even define, like, you know, currents mod more coefficient groups. And his idea was, well, let actually take directly, I mean, in the case of mod P, you don't have like a duality with differential forms, but we can always take this point of view, the one which is Caccioppoli style. That is, let us take what we think actually should be like classical surfaces mod P, and that's essentially easy. You just take linear integral combinations of smooth submanifolds, oriented submanifolds with boundary, and then you quotient mod P, and then let us close it in the appropriate topology. And the closure in the appropriate topology is going to be, like, you know, the concept of generalized surfaces mod P on which we want to build our theorem. And we can do that. So we can do that even though there is no functional analytic point of view. There is actually an homological point of view which is possible to take and which is very fruitful. So you can actually minimize and solve the Plateau problem even in the context of surfaces mod P. Particularly interested is actually the case of mod 2, in which all you're actually doing is you're allowing surfaces only to have multiplicity 1, but you're allowing them even to be non-orientable. Okay, so, and this also gives you a quite satisfactory theory. Okay, so this is all beautiful, and now when we come to kind of the second part of the talk, right? So the title of my talk was area minimizing integral currents and their regularity. And so now area minimizing, what we understand will be that, you know, they're a solution of the Plateau problem in this particular context. And what we're actually going to be bothered with is the regularity of this solution, which all this beautiful theory actually tells you it exists. So you can use Caccioppoli de Giorgi in codimension 1. You can use Federer and Fleming in a higher codimension and with integral coefficients, or you could use Fleming in any dimension and codimension and mod P. Okay. So that's the second part of my talk, and it is like, you know, what is the regularity? Okay, And here also I would like to, break down into some sort of, philosophical areas. So I want to talk about, okay, so first of all, let me talk about the very first starting point. So I will deal with so-called epsilon regularity, theorems, then like size of possible singularities, and for this I will actually go and have an excursion on tangent cones, and so area minimizing cones. And what I will call kind of, Liouville type theorems. So it will take me like a little bit to actually get to this point, why I'm actually using Liouville type theorems for this part of the regularity theory. And then, oops, this was an inadvertent push of the button in the tablet. I'm sorry for that. Okay, now I'm back, and even though being back, I should now share my screen again. Okay, yeah, here we go. Sorry for that. And then I will just talk about the issue of multiplicity and branching. Okay, so what are epsilon regularity theorems? So once again, you will pardon me if I go back to De Giorgi, but this was a development which was sort of independently made by Reifenberg in his own set theoretic approach, and De Giorgi in the functional analytic approach. But what turns out is that I think De Giorgi's point of view is actually taken much more often, simply because it's kind of more flexible, but it boils down to very similar philosophy. So let me start simply by the observation that as it happens for a measurable function, which, when you go to a course of real analysis, they tell you a measurable function is a function which, more often than not is sort of continuous. So, it has a Lebesgue point almost everywhere, for instance. So in some sort of measure theoretic sense, it's really close to be continuous. A rectifiable set, or, a rectifiable current, is in a sort of measure theoretic sense very close to BC1. And the replacement for a point of Lebesgue continuity in the case of real analysis for measurable functions are actually what are called generalized tangent planes to a rectifiable set or a rectifiable current. So the upshot is that almost everywhere in a measure theoretic sense, an integral current, without actually having to be minimizing, is flat at very small scales. Okay, and now you have to understand that just flatness must be understood in some integral sense. As it happens for Lebesgue points of functions f, you can't really just say that you have continuity. But for instance, what you could say is that if you take away a set of small measure, then the restriction on the function on the complement is actually continuous. Something very similar actually happens for currents. And now, the idea of De Giorgi was that once you have this information at very small scales, where you're actually approximately flat, your area functional that you're computing for your minimizer actually looks like, in first approximation, the Dirichlet energy. Okay, and the reason for this is the following. So if you have a graph f of a function, and you look at the m-dimensional volume of the graph of f, okay, that's actually going to be the integral over omega, and you're going to have the square root of 1 plus df squared, and then there are going to be higher order terms, which are at least quartic in the derivative of f. Now, this means that if the gradient of f is very small, so if you're approximately flat, if you're approximate like your tangent plane at that point, this functional is approximately the integral over omega of 1 plus the f squared divided by 2. And we know plenty of stuff about harmonic functions. So like, you know, the idea would be that a minimizer looks actually very close to an harmonic function. And since the minimizer looks very close to an harmonic function, I should be actually able to leverage that to some regularity theorem. In fact, what the Giorgi proves is some, you know, Morley-type decay of the appropriate integral quantity, and out of that, it just shows that at almost every point, you're actually going to be C1 alpha in the neighborhood of that point. In codimension 1, though. So that's very important, and it's in codimension 1 because there is one issue that I have to deal with, which in codimension 1 is much easier to deal with because you have the duality with sets, and that is the multiplicity issue. So I can't really expect that my surface looks like a graph, even approximately as a graph of a function f, only because I am actually flat in average. Because it might be that I'm in average flat, but maybe I am a multiple cover of the plane. Okay, and now it turns out that, you know, you can be in kind of, you know, branching cover of the plane by being area minimizing in higher codimension, and so you might actually have a situation in which you're in average flat but not that smooth, and that's because this picture is actually wrong, and because you cannot really describe your current efficiently as a single valued function. But it might actually happen. But this might not happen in codimension 1, where, like, you know, the fact that your graph or that your function is real valued gives you some sort of natural ordering of the sheets of a multigraph. Okay, so let me just be vague on this, but this is like what goes back to this epsilon regularity theorems, and these guys has been generalized in plenty of ways. So in fact, you don't need for this kind of idea to really have the area functional. It works for general elliptic functionals, and this was done by Algren almost immediately. You don't have to be really a minimizer. It's sufficient actually to be stationary, and there's wonderful work by Allard in the 70s, which is foundational for lots of geometric analysis applications. If you are in codimension 1 and you're stable, you actually get even like better property, and there's famous work by Schoen-Simon Yao and Schoen-Simon on this, and all along. So now, once you have this epsilon regularity, so the Giorgi was immediately able, and this was like, you know, published in an obscure way actually at the time, in a kind of a book in Italian, that if you have a minimizer in the Giorgi sense, you're actually smooth almost everywhere. Okay, now that's maybe nice, but I mean, it still possibly leaves you with a singularity of very, very high codimension. Okay, so how can I actually upgrade my size of the singular set for a minimizer? After all, I'm not expecting really that minimizers have such, you know, wide singular sets. And that actually leads me to point 2, and this kind of Liouville type theorems. Okay, so what could I possibly leverage to actually get me in this situation that I am flat at very small scales, and instead of just saying that this is happening almost everywhere, which is happening almost everywhere for any integral current without having to be minimizer, can I actually like use the minimizing assumptions to upgrade this almost everywhere flat into like, flat at really lots of points? And what can I do? Well, the first thing that I can do is a very natural, it's a first very natural thing that is the following. So I have my area minimizing current, say, I don't know how it looks like. And I fix a point over here. And what I can do is I can go over here, I can take actually a small ball, and I can like homothetically rescale the current. So like, apply an homotety and blow this ball much larger into something like this. And now look at what is happening to, your surface now. Okay, well, if you're hoping that your surface looks more and more tangent, what you could just do is you could actually send the radius over here. So this has, say, radius r. And of course, when I am blowing this to like, radius 1, what I'm doing is I'm doing an homotety of factor 1 over r. That's the dilation factor. So what I could do is I could actually send r to 0 and use the compactness, which I do have by my wonderful theory developed by the Giorgi, Federer, and Fleming, and like pick by compactness a possible limit of this. It's not hard to imagine that the possible limit of this is going to be area minimizing too. Okay, so something which you can imagine is like stable under passage to the limit, because if I land into something which is not area minimizing, I have a better competitor for it. And by some cut and paste argument, I certainly expect a better competitor for, the original surface, which cannot be. So now, what have I gained actually in this situation? Well, what I've gained is now a new information that I have, like a minimizer, but this minimizer doesn't have any boundary anymore, right? So because the boundary has been like pushed to infinity, so I have actually an entire solution, sort of the Plateau problem. Now, it's something classical that if you're actually looking at entire solutions of some PDEs, they usually enjoy, at least in some situations, if the PDE, for instance, is elliptic, much better properties than just solutions which have a prescribed boundary. So you expect some Liouville type theorem. So for instance, an entire solution of the Laplace equation, so an entire harmonic function which is bounded must be constant. That's the classical Liouville theorem. And you can actually ask what is going to happen if you have like, a global area minimizing surface. Is that actually going to be sort of, rigid? So for instance, one thing that you would ask is that actually going to be a hyperplane, right? So there are theorems like that. I mean, this is like a famous development in the history of the subject. It started with the classical theorem by Bernstein, who actually proved in the early 1900s that if you have a two-dimensional minimal graph in R3, that actually has to be a linear function. Okay, so it has to be like a two-dimensional plane. Now, what is actually what is actually going to be very beneficial in the context of area minimizing currents is something which is called the monotonicity formula. And the monotonicity formula actually tells you that the mass ratio of a current or a minimizing surface, so let me not go into the jargon. So if you have a sigma, which is area minimizing, and you intersect it with a ball of radius x, and if you look at the mass at the ratio of the volume in this ball divided by the power m of the radius r, so this quantity actually turns out to be monotone. And here it's actually not so long ago, a student asked me, who was the first one to find this out? And I honestly don't know. I can certainly tell you that it appears in the Giorgi's work, and it's not referenced. I mean, it doesn't give a reference anywhere. So at least he rediscovers it independently. And Now, so this gives you actually that this quantity has a limit at every point, but not only it gives you that that quantity has a limit at every point, it gives you that, you know, when you actually rescale and you look at your blown up surface that you get in the limit by this, you know, zooming in, it actually tells you that for the final surface, when you center your point X in the origin, where you might have thought of translating somehow the point you were like blowing up, this ratio is actually constant in R, which in turn implies that actually the surface is a cone. So not only you get an entire solution of the Plateau problem, but you have an entire solution of the Plateau problem, which is conical, which means it's like one homogeneous in the radial variable, which means that you got something which is like certain of complexity lower than what you had at the beginning, okay? So this led to a wonderful development by the work of several people, but it culminated in the famous work of James Simons, who actually proved that in codimension 1, so for hypersurfaces, any area minimizing oriented cone has to be planar up to dimension 7, okay? So in R7, area minimizing hypercones are flat necessarily. So this means that up to dimension 7, a codimension 1 solution a la De Giorgi is actually going to be flat at every point. In particular, his epsilon regularity theorem applies everywhere, and you're completely smooth. What happens when you go actually to 7 dimensions? Well, in R8, Simons himself showed that this cone cannot be shown to be, is stable. So if you want, Simons was using just second variation arguments to build this theory. And this cone actually has second variation, which is bigger or equal than 0, and he couldn't therefore rule it out. But not only he cannot rule it out because this guy is stable, it actually was proved by Bombieri, De Giorgi, Giusti, that in fact this guy is area minimizing. And so the regularity theory stops at that point. You actually have an example which is singular, but you could leverage all of this discussion, and this was done by Federer in what is called Federer's reduction argument. So you have actually a beautiful, a simple idea that by combining rescalings and the covering argument in a very efficient way, and the fact that you're conical, that it can't possibly happen that your singularities have actually more than codimension 7. So for the case of hypersurfaces, so the singular set of an m-dimensional area minimizing integral current has dimension at most m-7. Okay, and now this, like, of course, once you have this, you can start asking all sorts of questions. Okay, so this is like the first information. Can you give some structure? Can you, for instance, say that, you know, maybe it's an m-7 dimensional submanifold? Okay, we're very far from there. I mean, like, you know, things start getting really, really hard when you want to get more structures for these objects. But there have been, anyway, wonderful developments in the theory. So Leon Simon actually was first able to prove that, in fact, the singularities in this case, they are rectifiable. And there was a wonderful development after a long time by you know, groundbreaking works by Naber and Valtorta, in which they were able to show that not only they are rectifiable by different methods, I'd say more powerful than the one of Leon, or at least more flexible, maybe I should say, rather than more powerful, but it also has locally finite measure. But then it seems to be like very hard to go on this. Like, you know, could you, for instance, say that, I don't know, in codimension, so for 8-dimensional surfaces, area minimizing surfaces, that you have a 1-dimensional area minimizing, I mean, a 1-dimensional singular set, which looks like a tree, for instance, like, you know, some nice arcs which are actually joining. And it's not even clear whether we should, in fact, expect that. So then from here on, like, you know, this line of research has a big question mark. Somewhat in the same vein, let me also mention that once you actually do all these analysis, you know from the monotonicity formula, which is a very simple gadget, that at every point you do this rescaling, and even if the point is singular, up to subsequences, these rescalings, they're converging to area minimizing cone. But it's a compactness argument, so it's up to subsequences. If you're interested in the structure of singularities, one first question that you could ask is like, you know, is the area minimizing cone to which you're converging independent of the subsequence that you're taking? So, and this is called uniqueness of tangent cones. So this problem is called the problem of uniqueness of tangent cones to area minimizing currents, but you can pose it for, like, you know, stationary generalized surfaces, or for, you know, like stable and so on. And it's also widely open, except there's again a beautiful work by Leon, which actually says that in codimension 1, and then in higher codimension there are generalizations, but you're like going more. I mean, I would have to introduce more terminology, and I don't want to do that. But in codimension 1, area minimizing currents have unique tangent cones at every isolated singularity. And then he has deep works in when the singularities are not isolated, but there's no general theorem that would tell you actually that the tangent cones are unique everywhere. Okay, now let me actually get to the point 3. So far, as you see, I've actually carefully mentioned that every time that I say something, that we are in codimension 1, and I've also always carefully said that we are not minimizing mod p, for instance. I always said, you know, we're like integral currents. So I hinted at the fact that this powerful epsilon regularity theorem in higher codimension, but it's actually true even mod p in general, is obstructed by the fact that you actually have singularities in higher codimension, or mod p, at which the tangent cone is actually flat. So in higher codimension, and even in codimension 1, if you're looking at mod p, there are flat singular points. So situations in which you are in average flat, but de Giorgi's epsilon regularity theorem actually does not work. Okay, now let me give you 2 explicit examples for this. So this one is due to the combination of a classical fact in a complex differential geometry by Wirtinger, and a reinterpretation of it by Federer in the context of currents, So if I take this holomorphic curve in C2, or in general, if I take any holomorphic subvariety of a Keller manifold, so this one is an area minimizing current. So it's an area minimizing integral current of dimension 2 in R4. Okay. At the point 0, you see, so let me just call this like sigma. Of course, at the point 0, which belongs to sigma, there's no way I can write this as a smooth submanifold, right? So depending on which coordinates you have, if you're attempting, depending on which coordinates you choose, if you're attempting at writing your sigma as the graph of a function, you will discover that you need a multi-valued function, either taking 2 values or taking 3 values. Now, if I look at it though as, you know, a multi-valued graph of the function w to the power 3, and then I take a determination of the root of the square root, and I take the 2 branches of the square root lying on top of every point w. Now, if I look at it from this point of view, you see that there is this 3/2 exponent. When I am rescaling by a factor r in my zooming procedure, I actually get the following graph. So I get a prefactor, which is r to the power 1/2, and when I send r to 0, this is actually converging to z equals 0. So it's converging to a plane, but it's not a smooth point. Now, what is important though is that it's converging to a plane, but it has, like, you know, 2 points of top of the plane z equals 0. It's a double cover of the plane z equals 0, which means that it's actually converging in the sense of currents to 2 copies of the plane. And so here is why I said that in this philosophical situation for the currents, there is the issue of multiplicity. Okay, so that is obstructing the epsilon regularity theorem. I can't anymore just say that since the surface is flat, sufficiently flat in an integral sense at that point is a regular point. Now, in this particular case, you see that my surface has a branching singularity. And that's why in that point 3, I actually added branching to my philosophy. But it does not necessarily have to be branching. So here's another example. And this is actually by a pioneering work of White. So take 2 minimal graphs in R3. So take 2 minimal graphs in R3. Okay, and take, for instance, the first graph to be f equals 0, right? So like the 0 function, and take the second graph to be some local solution of the minimal surface equation. So G solving the minimal surface equation, which in this case is given by, okay, divergence of gradient of G divided by square root of 1 plus gradient of G squared, such that gradient G at the point 0 is equal to 0, and at the same times G of 0 is equal to 0. So there are plenty of them. I mean, you can just give explicit examples. Then the graph of F union the graph of G is not area minimizing. And that is like, if you want, you know, I could like shoot, I mean, I could use the Canon and like, you know, shoot at it with the George's theorem. But if you want, the reason why it's not area minimizing is because, like, the surfaces are crossing each other, and it's easy just to, give a comparison surface which is doing better, but it's minimizing what for? And in particular, it gives you an example of a singularity which is not of branching type for area minimizing Carvel's mod P, even in the simplest situation of two-dimensional surfaces in R3. Okay, so how do you get around this, actually? Well, this was maybe the greatest achievement of Fred Arnden. So around 1980, he published what is nowadays called his big regularity paper. And he gave what at the time was more than 1,700 pages proof that area minimizing integral currents have singular sets. Let me maybe add integral currents of dimension m have singular sets of dimension at most m-2. And you see this m-2 is actually matching exactly the example here, right? So this example over here has, or I should better say, maybe this example over here has a point singularity and is a two-dimensional example. And so from that point of view, his theorem is optimal. Okay, so now this was a very so this was for quite some time a sort of stumbling block if one wanted to go further, because it was a very difficult thing to penetrate. And there's plenty of questions that you could actually ask if you could go past this thing. So so in a series of works in 2015, 2017 with Emanuele Spadaro, so we worked hard to actually recast his theory in a more manageable framework. So so it's a more manageable proof. And there's plenty of questions that you could ask, but for instance, one that you would that I could immediately give you in the framework that we are in is well, once you have once you have actually dealt with the issue of multiplicity and singularities in the case of integral currents, can you actually deal, for instance, in the case of mod P? Okay, so and this is just an example of a simple question that you could ask actually right after you understand Arndt's theorem. So can you do something similar in mod P? Okay, and in the literature, there's actually a theorem by White which is showing that in codimension 1 and for odd P's, the answer is yes. But it's not really an answer to our question in the sense that if you are having actually an odd P, there are no examples of flat singularities. So it's still kind of difficult to get rid of the multiplicity, but the way he did it, it was like a very clever way to again fall inside kind of De Giorgi's epsilon regularity theorem. Although, don't get me wrong, I mean, it's a beautiful idea, and it's a subtle fact. I mean, just the fact that there are no examples of like flat singular points, it does not mean that it's actually going to be easy to get this theorem over here. But in a sense, I would just say it avoids still the issue of having branching and touching. And then again, White, through a powerful structural result, the answer is still yes for P equal 4. And of course, these actually are developments which came after the groundbreaking work by Gene Taylor, who in the 70s developed this fundamental regularity theory for, like, you know, soap-like, I mean, soap film-like solutions in 3D, and in passing, actually, for the case of P equal 3, proved R3 and 2D surfaces proved kind of, I mean, proves really what it is, a complete description of the regularity and of the singular set of your mod 3 minimizers. So it's really a beautiful theorem, just kind of a complete story on that. But the general case was open, and what we have actually been able to do, building on our understanding of Almgren's theory, is in fact the optimal result in that particular case. So in fact, this is kind of a recent theorem. So it's a recent theorem, which is a joint work by myself, Jonas Hirsch, Andrea Marchese, and Salvatore Stuvard. And in fact, this actually shows that for any P, any dimension and codimension, the singular set of an m-dimensional area minimizing current mod P has codimension oops, no, that's fine. Just go back. Of an m-dimensional area minimizing current mod P has dimension less or equal than m-1. Okay, and so I'm getting close actually to my the end of my lecture. And let just me say that this is just a glimpse of what you could actually do and ask. So let me give you two, like, you know, very interesting directions, which are at the moment completely open, or, you know, maybe not completely open, but we're just scratching just the bare surface of them. So one direction is boundary regularity. So we know full boundary regularity in the case of hypersurfaces. And actually, okay, so we know full boundary regularity in general by the pioneering work of Allard under geometric conditions. On the boundary. And boundary of multiplicity 1. And the geometric condition is that your boundary has to lie on the boundary of a convex set. Okay, then we know full regularity in codimension 1 without any assumption. and neither on the multiplicity nor on like, you know, any geometric structure of the boundary, just a little smoothness of the boundary. But in higher codimension, as soon as we like drop a large geometric condition or the multiplicity one, we know very, very little. And I mean, we just have partial results, very first partial results a few years ago. Well, in the last couple of years, actually. So that's one interesting direction. Another interesting direction is now that we have the size boundaries, is like, what is the structure of the singular set? When flat singular points can occur. And again, I mean, the first question that you could ask is, can we at least get the same the same rectifiability theorem that was proved by Leon Simon in his pioneering work in codimension 1, and which was actually improved by Naber and Valtorta to rectifiability and finite measure very recently with their powerful technique. And I mean, in all of these cases, like what you're leveraging is the monotonicity formula and the structure of a cone. And that is, for the moment, not there in our analysis of the singularities, which have flat tangent cones. So this is also widely open, and we're just, again, just only scratching the surface of the problem with some partial results. So let me just close over here. So in particular, rectifiability. Okay, and with that, let me finish my talk. Thank you for being with me for this long run, which I hope it has been at least some fun for you as it has been fun for me.
All right, thank you, Camillo. That's wonderful. Could we maybe give Camillo a round of applause, if you don't mind doing that? So if there are any questions, please raise your hand. I have one.
Or you can use the group chat. Yes.
Camillo?
Yes.
Have you thought about minimal Lagrangian submanifold?
I have, and I am. And there's some more that you can say in that occasion. Yeah. But for the moment, I cannot tell you. So I have some interesting ideas if you want, but for the moment, I cannot tell you that I have any theorem. There's a PhD student. There's a PhD student of mine who's trying to get kind of interesting examples with interesting singularities in that case. So there's some development. You definitely can see that there is some structure that could help.
Right. That would be very interesting to understand them. In relation to mean symmetry.
Yes. So one thing that I've like suggesting to a student of mine to look at is whether I mean, it's what more can you say about the linearization? So Armand's theory goes through the linearization of the area functional with multivariate functions. Mm-hmm. If you're minimal Lagrangian, your linearization actually has more structure. So one thing I've asked actually a PhD student of mine is try to see if there's something that can be done in that direction. But for the moment, I don't have any good development that I can tell you. Maybe in a year or so.
Okay. Okay.
So Camillo, I have a question. In the mod P regularity that you did it at the
Yes.
very for all P. So first, is that over a dimension reduction, or are you ruling out certain cones to get the regularity?
No. So, okay, so that is the first step you do. And then once you've done the dimension reduction, you've got two problems. So, okay, so you've got essentially one problem. So the fact that a flat tangent cone is actually not giving you regularity. So the dimension reduction actually works very well. And if you're using neighbor Valtorta, actually the dimension reduction even tells you that where you see bad cones, that's a rectifiable set. But now what you actually would like to do is to exclude actually that there are too many singular points where you have a flat tangent cone. And that's what we're able to do.
Okay, and the flat there is with multiplicity, and so presumably. And
the flat there is with multiplicity, right? Exactly. So the very example that I gave you by Brian, which is like, you know, the union of these two surfaces gives you an idea of what might happen. Like, you know, you might have a very high order of contact between two minimal graphs, for instance.
And can you give an idea as to why that, you know, what is it that's making that not happen?
Okay. It's not happening at too many points. You know, in this particular situation, if you're looking, okay, so if you're looking at this, I mean, you can match, okay, so like, you know, the intuition would be the following. So if I were even really to tell you that, for instance, mod 4, you can decompose it into, you know, union of graphs, which is actually what Brian is essentially able to do mod 4, but then there's no such theorem higher moduli, like, you know, 6, 8. So you see that the point which bother me are the point where the value of the function is equal to the value of the other function, and the point where the gradient of the function is equal to the gradient of the other function, right? So like the bad points are the nodal set, if you want, of the function g. And now if you're solving an elliptic PDE, like these guys do, of course, the nodal set cannot be too large, right? So in fact, typically these flat these flat singular points must have codimension 2. So as soon as you go a little bit away from the 0, these two functions g and f, they're actually crossing each other. So they're forming singularities where the tangent cone is actually two crossing planes, okay? And for those, you have the dimension reduction, and you can say that is actually a codimension 1 stuff.
Okay, thank you.
It makes you hope that in those cases, you can actually prove rectifiability, and that's what we're trying to do right now.
Great. Very nice.
Thanks.
Well, I guess if there's no more questions, do we just thank Camillo? Okay, thank you very much, Camillo.
Thanks to you.
Thank you, and have a great day.
Yeah.
Bye, you too, guys.
Bye.